All right, welcome to Étale Chromology on December 1st, 2020. It's December now. I hope you all had a good Thanksgiving break, those of you who are in the US and celebrate Thanksgiving. So a brief announcement. So UGA is on the schedule is sort of unusual next week, which means that actually this Thursday, so Thursday is the last official class. So if you're registered for the course, you don't have to come after that. And if you're not registered for the course, you don't have to come after that. So that means that today is the second last official class. So I'm going to keep going until we at least more or less give the proof of the Riemann hypothesis, modulo some details. At least I actually think there's a chance we'll get there. Depending on how much we manage to cover today, I think there's a chance we'll get there by the end of tomorrow, by the end of Thursday. And then I will do at least one extra class on kind of applications of the Weil conjectures in Weil 2. But again, no one is obligated to come to that, and I'll make an announcement about that on the Discord. So if you're not on the Discord, let me know, send me an email, and I'll send you an invite so you can make sure you're up to speed on that. And I'll also put something on the course website. So the class will probably not end completely on Thursday, but we're winding down now. If there are any particular extra topics you would like to see, please let me know, and I'll see what I can do. So in particular, one thing I'm thinking about doing is explaining the proof of the Chebotarev density theorem for varieties over finite fields, which is a pretty nice, easy application of the Weil conjectures. And then I might talk a little bit about formality of varieties of smooth projective varieties over finite fields, if there's interest in that. All right, are there any questions before we return to proving the Riemann hypothesis? All right, if not, let's get started. So let me remind you what we were doing. So we were proving this main lemma, which I could copy and paste from the previous notes, but instead I want to write it down so that you guys actually remember what we're trying to prove rather than copying literally a page of text and then reading it rapidly. So let me remind you the setting. So X naught subset was an open subset of P1 over a finite field. And X was its base change to FQ bar. E was a locally constant QL sheaf on X naught. And then capital E was the corresponding pi1 representation. And we had a bunch of assumptions on this sheaf E. So first of all, we assumed that the Frobenius action on the fibers of E, on the geometric fibers of E, had rational characteristic polynomial, meaning the coefficients are rational numbers for all closed points X in capital X. So 2, we assumed that there was a non-degenerate skew-symmetric form. C from E times E to QL of minus n for some n. And then 3, we assumed that the image of pi1x so it lands inside of the symplectic group of this psi, so the group of automorphisms of E, which preserves psi. So why is that? Well, because this is supposed to be a skew-symmetric, a map of representations, and we assume that this had open image. Then there were 3 consequences. So A was that E has weight n, and what that meant was that that the Frobenius action on E X on this fiber had eigenvalues alpha such that the absolute value of alpha, so these are algebraic integers or algebraic numbers by 1, and their absolute value is q to the n times the degree of x over 2. So this is what it means to have weight n. And here, again, let me remind you, so alpha is by assumption an algebraic number, and this absolute value means absolute value for any embedding of the field alpha generates over q into the complex numbers. Okay, B was the statement that if you look at the action of Frobenius on the compactly supported cohomology of X with coefficients in E, this has rational characteristic polynomial. And the eigenvalues, which are by assumption algebraic numbers, satisfy that their absolute value is at most q to the n over 2 plus 1. And then C was that the Frobenius action on now just the ordinary compactly supported cohomology of P1 with coefficients in j lower star of E, where here j x to P1 is the natural embedding, has a rational characteristic polynomial. And the eigenvalues gamma satisfy that the absolute value of gamma is between q to the n over 2 and sorry, these should be less than or equal to, between q to the n over 2 and q to the n over 2 plus 1. All right, so those are, that's our goal. So we started proving A last time. So let me remind you where we were. Yeah, well, maybe let me just remind you a bit of the context. So the context was that we were imagining we had a family of varieties fibered over P1. Those varieties had the fibers of this map had an odd dimension, and then this E was supposed to come from the middle cohomology of those fibers. So in particular, such a thing has a natural symplectic pairing on it given by cut product. And we know that cut product is not degenerate by Poincare duality, and it's skew symmetric because we're in odd degree, because n is odd. So typically, kind of in real life, so 1 and 2 will be satisfied for just the middle cohomology of a family of varieties, and 3 will not. 3 is more special. Sometimes it will be satisfied for nice families, but what we're going to do is we're going to find the kind of subspace of the middle cohomology of a family of varieties satisfying this 3, and that will be given to us by the theory of Lefschetz pencils, which I explained a little bit about last time, and we'll explain more about after we finish proving this main lemma. Okay. So last time we began the proof of A. So last time we reduced the proof of A to the following 2 statements. So first of all, we reduced it to lemma 1, which was that if you look at the 2k tensor power of E and take its pi1 co-invariants, this will be a direct sum of copies of QL twisted by minus kn, so a direct sum of some number of copies. And lemma 2 was that if for all k, the zeta function of x given by the sheaf e to the tensor 2k t, so this is the sheaf from lemma 1, converges for t at most 1 over q to the k n plus 1, then E has weight n. Okay, and let me just briefly remind you how the how reducing A to these statements worked. The point was just that lemma 1 implies the hypothesis of lemma 2 just by analyzing like the implications this has for the cohomology of e to the tensor 2k. Essentially, this controls the H2 with compact support of this sheaf, and then H1 was not so hard to understand more directly. So H1 sort of appears in the numerator of the zeta function, and then H2 appears in the denominator. So it's what controls the radius of convergence. So the point was that 1 implies the hypothesis of lemma 2, and then what we're trying to prove is the conclusion of lemma 2. All right, so let's prove these lemmas. Are there any questions about what we're trying to do right now, or about the general structure? I mean, this is an extremely complicated proof, so if you want me to step back and sort of say anything about the structure, like now is a good time to ask me about it. Okay, I mean, that said, like this, where we are now, I mean, these sorts of statements are actually more or less formal. There's no geometry in these statements. All right, so let's begin. Let's prove lemma 1. Okay, so this let's actually just make some elements of the invariance, of the co-invariance rather. So does anyone see any natural let's first just so let's first consider the case where k is 1. So let's first consider this case. So does anyone see any natural co-invariance of E tensor E? So if we just want to compute what these are, we might as well, for example, compute Hom E tensor E Hom E tensor E let's say QL, and this is as pi1 x representations, and here pi1 it means pi1 x, not pi1 x naught. So this any map to QL factors through the co-invariance. So this is the same as Hom pi1 of x E tensor E co-invariance QL. So both of these are trivial pi1 reps. So now we can drop the pi1 of x, right? This is just Hom E tensor E pi1 of x co-invariance into QL. Does anyone see any maps like this? So let me give you a hint. This skew symmetric form here looks like 1, right? Do you see why this gives you a map from the co-invariance to QL? Does anyone have any questions about this or any thoughts? The form is bilinear, right? So it gives you a map out of the tensor product. The fact that map is pi1 invariant means it factors through the co-invariance. Okay, and then I claim in fact that this is equal to the span of C. Okay, and why is that? So this equality follows because pi1 has dense image. In SP, E, C. So in particular, co-invariants are something that are insensitive to passing to Zariski closure. So what this tells you is that so the co-invariance of, I'm taking co-invariance as like an algebraic operation, but it's insensitive to passing to closure. So the co-invariance of pi1 of x are the same as just the co-invariance of SP. Okay, and this is now a formal linear algebra statement. So I'm not going to prove it, But now the claim is that if you have a symplectic vector space, then any map out of its tensor square, which is covariant, is of the set. Okay, so let's try general. We're like, okay, well, we can say pi1 covariance, but we might as well just say SPV C covariance into QL. Okay, and again, this is now a linear algebra statement. The claim is that the span of the following thing, you take the product of k copies of C V1 VI1 VI2. So meaning there's a sort of clear way you can make elements of this co-invariant. You just take you just divide these 2k copies of E into pairs, and you plug each of those pairs into C, and then you multiply them all together. Okay, and then the claim is that these span actually the whole co-invariance, and again, this is a linear algebra statement about co-invariance of the symplectic group. It's not a totally trivial statement, but it's not algebraic geometry, so I'm not going to prove it in this class. Okay, and now why is the Galois action correct? So this gives you a bunch of copies. So this is QL to the minus KN to some power. That power really actually just depends on the dimension of E. So that's some abstract linear algebra invariant. This is because each copy of C contributes a QL of minus N, that's of C, and then we're multiplying K of that, so you get a QL of minus KN for each of these forms. All right. Are there any questions about this lemma 1? So the point is that ultimately this was sort of formal from the fact that the image of pi1 was dense in SP of C in the symplectic group of C. Great. Are there any other questions or any questions? All right, so now let's prove this lemma 2. So let's understand the radius of convergence of these zeta functions. So we want to show that if the radius of convergence is large in some fairly weak sense, so just large means that it converges in this radius, where here this radius is getting bigger as k is getting larger, then we win. Then we understand the eigenvalues of Frobenius on the fibers of this the fibers of this sheaf, the stalks of this sheaf. All right, so let's understand why that's true. So first of all, we need to use the sort of Euler product of these zeta functions. Sorry, so the zeta function as the following in the following x u, the closed points of x of 1 over the determinant 1 minus the Frobenius of x times t, acting on sorry, this should be t to the degree of x, acting on the fiber of E to the tensor power. What does this imply? So here we're taking a product of rational functions. This product will, if this product converges, then each of these rational functions has to converge. So what that tells us is that so the hypothesis implies that each of these 1 over the determinant of 1 minus the Frobenius at x times t to the degree of x on ex to the tensor 2k converges for absolute value of t less than what we said, 1 over q to the kn plus 1. All right, so what does this imply? This implies that each of the eigenvalues. So what are the poles of this? So the poles of this are 1 over the eigenvalues. Each of the eigenvalues of Frobenius satisfy the absolute value of Frobenius of the absolute value of the eigenvalue. Sorry, is at least q to the let's see. I think we get q to the degree x times kn plus 1. Okay, and now the point is, so what are these eigenvalues? So when you take a tensor power here, you just get a product of the eigenvalues that occurred on E. So this is again another example of the tensor product trick. So the tensor product trick now gives you so that just lets you kind of divide by k. It gives you that alpha is at least q to the degree of x times n over 2. Okay, so this is half of what we wanted to prove. So we wanted to show that that this absolute value equals this number. But there's a pairing here, right? Which tells you that you can also flip this inequality, like just by replacing E with its dual, which is isomorphic to itself. So dualizing replaces the eigenvalues with 1 over themselves. And this the pairing, so now gives you the other inequality. All right. So that's the proof of part A of the lemma. So ultimately it was pretty formal. So what did we use? So we used and we used all the hypotheses. So we used this to even make sense of the statement, to say that we have kind of rational or algebraic numbers here. We used this to understand the invariance, and then the last step was a sort of just basic analysis, plus again using this pairing to turn one inequality into the other inequality. Okay, so we've proved A of the lemma. So let's start proving B. Are there any questions before we start doing that? Okay, so what do we want to do? We want to understand the action of F on the compactly supported cohomology of X, our open subset of P1 with coefficients in E. So there are 2 steps. We need to show it has rational characteristic polynomial, and then we need some bound on the eigenvalues. So let's start doing that. So let's start proving B. So first of all, what are we trying to understand? So one way of saying what we're trying to understand is we're trying to understand the zeta function of x naught e t. So this is what we're trying to do in particular is we're trying to understand the zeros of zeta function, right? So those are controlled by one of the one supported of x with coefficients in E by the Lefschetz trace formula. So understand this. So this is controlled by HI with compact support of XE, and by the Frobenius action on this, and we're interested in H1. So let's try to unwind what these groups are and then use the product formula. So first of all, let's try to consider H0 compact support XE. So can anyone tell me what this is? So my hint is remember that X was assumed to be affine.
But then it's 0.
Yeah, so it's 0 because there's no compactly supported cohomology in degree 0 on an affine. So H2 compact support XE. So this we computed last time via Poincare duality. This is E pi1 co-invariants twisted by -1. So what is this? So this is the same as the co-invariance of the symplectic group, because pi1 is dense in the symplectic group. So in other words, I'm asking what are the co-invariants of the standard representation of the symplectic group? Any thoughts? Okay, so this is just 0. So I mean, I guess this is a direct computation, but an easy proof, for example, is that the symplectic group is generated by transvection. So sort of things that look like 1, 1, 0, 1 in a little square. And if you just share those, it's not so hard to see that there are no co-invariants. Those themselves sort of span all of E. All right, so what that means is that this zeta function, x naught E t, is literally just the characteristic polynomial of Frobenius on the group we're interested in. So all we want to do is understand the zeros of this zeta function. There's another way we can write this. We can use the Euler product. So this is the product of x, or the closed points of x, of 1 over the characteristic polynomial of 1 minus the Frobenius at x times t to the degree x, evaluated at on the stock of E at x. Okay, so by assumption, so the assumption was that these characteristic polynomials have rational coefficients. These have rational coefficients. So if you expand this out in a Taylor series that says that this characteristic polynomial has rational coefficients, this implies that the determinant or t on the compactly supported cohomology of x with coefficients in E has rational coefficients. Okay, so the content, so what have we shown? This is the first half of what we wanted to prove. What's the point? The point was just that we knew this zeta function had rational coefficients by assumption, so just by this Euler product. And then what we had to show is that there was no weird cancellation. So a priori, this could have been really horrible. Like it could have had some non-rational coefficients if whatever non-rational factor of it had been canceled out by something coming from H0 or H2, but those groups were just 0. So we're okay. So now we want to understand the eigenvalues of the roots here, and it just by more or less the same argument as in lemma 2. So to understand the eigenvalues, it suffices to show just by taking 1 over this picture, it suffices to show that this product 1 minus fx t to the degree x on ex, so this is just 1 over this picture, converges. So this is an infinite product, converges for the absolute value of t less than 1 over q to the n over 2 plus 1. So why is this? Understanding the zeros of Frobenius here is the same as understanding the radius of convergence of 1 over this polynomial. And 1 over this polynomial is the product of these polynomials, at least where both sides converge. So if we can prove this inequality, if we can prove convergence in this region, then we've shown that there are no poles for 1 over this polynomial in the same region, which is what we're trying to. All right. Are there any questions about? Maybe this should say to understand the eigenvalues. So are there any questions about the strategy for the rest of the proof of part B? All right, so let's give the sort of zeros of this like let's sort of try to understand this more explicitly. So let's let ai comma x be the eigenvalues of the Frobenius set x acting on the fiber of E at x. So what is this determinant? So this determinant is like it's like a power sum of the eigenvalues. So I claim it's enough to show that the sum over I and x of these aix times times t to the degree x converges for absolute value of t less than in this region q to the n over 2 plus 1. Okay, so why is this? This is just from expanding this product out. So this product is like 1 minus the eigenvalue times t, and if you expand that out, you get a sum like this. Okay, so this is something we can do by bounding these alpha i's and then also just the number of points of degree x. So this is going to follow from 2 things. So first of all, let's understand these AIs. So this absolute value of these AIX's is actually, we know what it is. So it's equal to q to the degree x times n over 2. Can anyone tell me why this is? So let me remind you, these are the eigenvalues of Frobenius acting on the fibers of this sheaf, which is something we understood from A, right? So this was literally the output of part A. And then 2 is a little simpler. So the number of closed points of degree m is less than or equal to q to the m. Can anyone tell me why this is true? So maybe I'll give you a hint. So X is a subset of P1, open subset of P1, and it's affine. Any thoughts? Okay, the point is that
it's just the like total number of, it's like the max number of possible degree m points in general, right?
Yeah, exactly. So P1 has q to the m plus 1 points.
Yeah.
You deleted at least 1. So strictly speaking, this could be, let me just put a plus 1 here. It won't actually matter, and then it's obvious. So strictly speaking, this is only true for large M, because maybe you delete, instead of deleting a rational point, you deleted a bunch of Galois conjugate points which are not rational. So it could be that there's still q plus 1 rational points. But yeah, but this is true and that suffices. Okay, and then I'm going to leave the actual analysis as an exercise. So you plug these 2 facts into here, and you win. So now, yeah, I don't think you want to see me do the analysis. All right, so let's now prove part C. So let me remind you what that said. So this is not, C is quite easy from what we've done. So here we've now analyzed the compactly supported cohomology of E on our open subset of P1. And we've bounded the eigenvalues here from above. Now we want to understand the cohomology of the push forward to P1, which could be, it's not so, it could be a little wilder. But nonetheless, we'll be able to bound the eigenvalues, and we'll say that they're between q to the n over 2 and q to the n over 2 plus 1. Are there any questions about this last step, like what we want to show? Oh yeah, and we also want to show that the characteristic polynomial has rational coefficients again. So yeah. All right, so let's understand this. So how do we relate the cohomology of the compactly supported cohomology of E to the cohomology of the push forward to P1? Does anyone have any thoughts?
I think we had some short exact sequence relating them.
Yeah, there was some exact sequence. So yeah, let's write out what it was. So first of all, how do we compute compactly supported cohomology? What we do is we extend by 0 to all of P1. And this maps to the push forward. So this is the sheaf whose column we're interested in. And what is the co-kernel of this map? So this map is on stalks. This is an isomorphism at points contained in X, and it's just 0 map, and because this left-hand side is the zero sheaf on points not contained in X. So can anyone help me write down the co-kernel of this map? Let me give these maps some names. So we've X naught goes inside of P1 via J, and then let me call the complement P1 minus X naught, which is a finite set. I'll call its inclusion I, or finite scheme. So one way of writing it is just we want to take, it's the skyscraper sheaf whose stalk at it's a direct sum of skyscraper sheaves concentrated on P1 minus X naught, and the stalk is just the same as the stalk of J lower star of E. So one way of saying what that is we can take I mean, I'll just write it and then I'll explain what it means. So what this is so we just take whatever J star of E is, we pull it back to the complement. So that's where this map is not an isomorphism, and then we push it back forward again. Okay, so one can check directly on stalks that this is a short exact sequence of sheaves, and then this is a skyscraper. All right, so what does this tell us? So the long exact sequence in cohomology tells us that we get a map from H0 of the skyscraper sheaf. So this is all on P1 of I lower star, I upper star, J lower star E. This goes to the compactly supported cohomology of X with coefficients in E, which is just the same as the cohomology. So this is equal to the cohomology of P1 with coefficients in J lower shriek of E, just by definition. And then this maps to H1, P1, J lower star of E. Okay, then the cohomology of skyscraper sheaf is 0. Here, all of these cohomologies are over FQ bar. Maybe let me write that as FQ bar. Okay, great. So what we're interested in for this part of the lemma is this group. We're trying to show that it has rational, that the Frobenius action on this group has rational characteristic polynomial. and that its the roots of that polynomial, so the eigenvalues of Frobenius, satisfy some inequality. This is what we studied in part B. So anyone now why the eigenvalues of Frobenius here have rational characteristic polynomial. So we want to show that the Frobenius action on H1 of P1 of Q bar, J lower star of E, has rational characteristic polynomial. So that's the first thing we want to prove. Any thoughts?
Can't you just push the result from H1 compactly supported to this one because of the long exact sequence?
Yeah, so there's a slight subtlety here. That's absolutely the right idea. So the issue is that these are not Q vector spaces. If the roots of this polynomial were, let's suppose the characteristic polynomial was irreducible over Q, right? Then if these were Q vector spaces, you'd win. I mean, in fact, this map would have to be an isomorphism if the characteristic polynomial was irreducible over Q. But they're QL vector spaces, so a priori that the characteristic polynomial could split over QL, and maybe you could just be projecting onto one eigenspace, right? Like onto the eigenspace of some alpha, which need not be a rational number. So one needs a teeny bit more than just the fact that this is a surjection. Does anyone see what it is? So what is it? So the characteristic polynomial, let me write it this way, characteristic polynomial of Frobenius on H1, P1, FQ bar, J star E. So what it is it's the characteristic polynomial, but maybe let me write for this is H0 of some stuff. So what it is it's a characteristic polynomial on H1 compactly supported, sorry, of Frobenius on H1 compactly supported XE. So this we know is rational, as Jose pointed out, and then it's divided by, let me call this map delta, it's divided by the characteristic polynomial Frobenius on the image of delta. So we almost win here. So if here, this is the characteristic polynomial Frobenius acting on the stalks of our sheaf E, which we know by assumption are rational numbers. So if this map was injective, we'd win. So what you actually have to do is you have to continue this sequence to the left. So you have to right here, we get H0 of P1, J lower star of E, and then before that is 0. So what you get is actually the characteristic polynomial here. We have to multiply by the characteristic polynomial of H0, P1, J lower star of E. Okay, and now maybe I'll leave this last step as an exercise, but so both the rationality of this and this follow from the assumption of rationality on the fibers of E. So here, what you'll see is that this sort of fills in the gaps of that are arising here. There's a little bit of analysis with the inertia, which we'll see maybe some version of in a little bit. So I won't do it quite yet. Okay, so this is supposed to be rationality. So now let's try to do the inequality. So let's now try to do the inequality. So let's try to show that we want that if alpha is an eigenvalue, we want q to the n over 2 less than or equal to absolute value of alpha is less than or equal to q to the n over 2 plus 1. So does anyone see one of these bounds is immediate? So this bound is immediate from B. So why is that? Well, it's because of this surjection. So any eigenvalue that shows up here all has to show up here, and we just showed that the eigenvalues here satisfy this inequality. So the other inequality will follow from Poincare duality. So Poincare duality will give a perfect pairing let's see, between between H1 P1 J star E and H1 P1 J star E dual of 1. This lands in H2 of P1 with coefficients in QL of 1. And then okay, now you have to, the point is that this sheaf E dual of 1 also satisfies the same hypotheses as the original sheaf, and one applies the statement there. So that will give the other bound. So apply the result, apply upper bound, the upper bound to E dual of 1 for the result. So that modulo, okay, so modulo two things. So modulo this and modulo this pairing finishes the proof of the main lemma. So I want to talk about this pairing first, and then I'll talk a little bit about understanding this piece of the zeta function. All right, are there any questions before I move on to understanding that? Okay, so what I want to do is just briefly talk about sheaves of this form. So push forwards of constant sheaves from an open of a curve to the whole curve. So let's just briefly try to understand J lower star of E for E, a locally constant sheaf. So here's the proposition, which I will not prove, but I will explain briefly where the proof comes from. So again, suppose we have let me maybe state it in slightly more generality. So suppose U of Y is a affine open inside of a smooth, proper, geometrically connected curve over an algebraically closed field. And suppose lambda is just either Z mod L to the NZ or QL, where here L is not equal to the characteristic of K. Then I just briefly want to understand something about push forwards of constant sheaves from U to Y. So suppose F is a sheaf. Is a sheaf of lambda modules on Y. So we want to understand, well, when is it a push forward from U? So A is it's a complete characterization of that. So being a push forward from U is just the same as having the following property. So you're isomorphic. Well, if you're the push forward from U, we know what you are on U, right? So you can just pull back to U and then push forward again. So you want this natural map to be an isomorphism. This natural map just comes from a junction of lower star and upper star. So this is an isomorphism. Only if the following two properties hold. So for all S in Y minus U, the co-specialization map fs to f, here these are geometric points, to fs eta bar is injective. And then 2, the image is the well, if we look at f eta bar, so this is a Galois representation of the function field of your curve, and that function field has inertia groups corresponding to each of the punctures, and we want the image to be the invariance of the inertia group at s. Okay, so this is a local computation. Okay, and then B, so for locally constant f, which is a QL sheaf satisfying, sorry, this is not correct. So for f a QL sheaf satisfying the above, and locally constant on U, well, there's a cup product pairing from HR of Y load star of F times H2 minus R of Y with coefficients in J lower star F dual twisted by 1. And where does this land? This lands in H2 of Y with coefficients in QL of 1. Okay, and the claim is that this is perfect. So this is what we used at the end of our proof of C. This is a perfect pairing. Okay, so B just comes from it's a fairly soft application of Verdier duality, which I at least stated and said a little bit about earlier. And then this business, so understanding the image of delta here, this image of delta is more or less the images of these co-specialization maps in each of these fibers. So unwinding why this is rational is more or less this part A. So I'm not going to give any more details about that, but if you should try it on your own, and if you have trouble, we can try to work it out in office hours, which I will put an announcement up on. Is that A is a local computation. So this you can compute at the strict cancellation of S, and then B is an application of Poincare duality or Verdier duality. All right, so this concludes the sketch proof of the main lemma. So now we're going to start. So are there any questions before we start doing that? So my goal is sorry about that. I don't know what just happened. I guess
it was getting very choppy. Yeah, and then I guess I kicked you out or you dropped out.
Let's try again. So what was the last thing you all heard?
I heard you asking if there were questions, basically, and then it started cutting out for me.
I see. Okay, well, hopefully. So are there any questions, I guess? Is it better now?
Yes, definitely.
Great. So are there any questions? All right, so if not, we're going to start talking about Lefschetz pencils. So I want to now go back to discussing Lefschetz pencils and explain exactly. So at the end of last time, we explained kind of the general strategy, and now we're going to start executing it. So let's talk about the cohomology of Lefschetz pencils. So honestly, I would love to just teach a whole course on this. So unfortunately, we're not going to be able to do that. But I'll at least kind of try to tell you the basic facts and indicate how one might do them. And the reference for all of this is SGA7. So let me just briefly remind you what the situation was. So X is going to be a smooth projective variety. So with a fixed embedding in projective space, and then L inside of the dual projective space was going to be a Lefschetz pencil, which means a family of hyperplanes with some nice properties. So in particular, the base locus of the family intersects X transversely, intersecting with X are mostly smooth, so all but a finite number are smooth, and the singular ones have a unique ordinary double point, which means there's a unique singular point, which looks like the cone over a non-degenerate quadric. So that's what a Lefschetz pencil was. So to this data, one can associate the family of hyperplane sections. So family xt to L. So this is just P1. So this is a family of such that with the following properties, such that the generic fiber is smooth, and the singular fibers have unique singular points, have unique singularities, which are ordinary double points. And let me just briefly remind you, I mean, what this xt was explicitly is it's the blow up along the base locus of L intersected with X of X. So this we discussed when we sort of discussed Lefschetz pencils last time. So what I want to explain is what the cohomology of the fibers looks like as a local system over the locus where this family is smooth. And I'm going to make an assumption. So I'm going to let S subset P1. We're going to let this be the set of points of T in P1, such that xt is singular. And I'm going to assume the fiber dimension n is going to be some 2m plus 1. So in particular, it'll be odd. So what you should think is that the total space of this family is an even dimensional variety. So the fibers are going to be odd dimensional. And let me remind you that very early on, so maybe 2 weeks ago, we reduced the proof of the Riemann hypothesis to understanding something about the middle cohomology of even dimensional varieties. So what we're going to do is, and this we discussed at the very end of Tuesday, so a week ago, what we said is that we were going to try to compute the middle cohomology of this variety using the Leray spectral sequence. So that will boil down to computing the cohomology on P1 of some middle cohomologies of some odd dimensional varieties. So those things will have a symplectic pairing on them, and we'll try to apply the main lemma. Okay. Sorry, I'm trying to get my notebook to stay open here. So I'm going to let U be P1 minus S. So this is the locus where my family is smooth. And then I'm going to let IS be the tame inertia at the point S. And I'm going to let V be the middle cohomology. So I'll call this map pi of the local system given by the middle cohomology of the fibers. And if you'd like, we can even think of it as the representation of the Galois group of the function field of P1. So this is what you should think of it as the monodromy representation of this family. And by smooth and proper base change, so over U, this push forward sheaf is a local system. Okay, so here are a bunch of claims. So I want to describe some facts about the cohomology of this family. So first of all, so in almost all degrees, this family, like the push forwards of these, the push forwards of the constant sheaf from this family are actually going to be constant. So sort of the only interesting dimensions will be the sort of the middle ones. So for r not equal to n and n plus 1, where here n was the fiber dimension, the claim is that the derived push forward of the constant sheaf QL, the rth derived push forward, is actually locally constant. And then hence constant. So I'll say a word about this. So what is this saying? It's saying that the singularities in these fibers are so mild. So if this family, like if all the fibers were actually smooth and projective, this would be true in all degrees by smooth and proper base change. So what this is saying is that the singularities of these fibers are so mild that they're only being seen in 2 degrees. So that's going to imply locally constant. So that's a local computation about ordinary double points, which I'll say a little bit about later. Then constancy actually follows from the fact that pi 1 of P1 is trivial, which I haven't remarked. So any finite cover of P1 is just a disjoint union of copies of P1, at least geometrically. All right, so B, if we look at Rn pi lower star QL restricted to U, this is locally constant and tame. So what that means is that the action of wild inertia at these points, at the singular points, is trivial. So this is, again, a local computation about ordinary double points. It's not at all obvious. Okay, C. For each S in S, so for each point where this fiber is where the fiber is singular, there exists a so-called vanishing cycle. Delta S inside of V of M, so this is inside of the generic fiber of this local system, twisted by M, well defined up to sign. Satisfying some properties I'll define in a second, but one definition of this, at least up to scaling, is that the span of delta S is going to be dual to the co-kernel of the co-specialization map. From Vs to V eta bar. So in particular, the claim is that this map is injective, which I'll discuss in a little bit, that its co-kernel is one-dimensional. And now Poincare duality says that this is dual to its twist by M, where, let me remind you, M was kind of approximately half the fiber dimension. So the fiber dimension was 2M plus 1. And so if this co-kernel is one-dimensional, that means that the dual of this is a canonical one-dimensional subspace. Okay, and but there's a further claim here, namely that this subspace is generated by an element, which is like a kind of canonical element, which is well defined up to sign. So I'll discuss that in a little bit. So D, okay, so let's briefly say what's happening here, so we can make this a little bit more explicit. So there's 0, we have this exact sequence 0 to hn of xs ql. So this goes to hn of x eta bar ql. So this is the co-specialization map. And now my claim was that this maps to ql of m minus n, and then this goes to 0. So this map is going to be cupping with this class from before, and the claim is that this is exact. Okay, so the content here is this somehow C and D are the same. So the content here is identifying this co-kernel with cupping with the with delta S, and this is how. So what I'm trying to do is I'm trying to give a sort of soft description of these vanishing cycles, but identifying this map with cupping with delta S is what pins down delta S. Okay, and then finally, E. So how does like what is the representation on this V eta? So if we're given sigma S in this tame inertia group at S, so tame inertia is isomorphic to the product of L not equal to the residue characteristic of ZL of 1. And let me call TL the natural projection to ZL of 1. So then given given X in V, so this is the generic stock of this local system, we want to know how does this tame inertia act on X? And it acts in a very predictable way. So what it does, it sends to X plus or minus TL of sigma S times X cup delta S. So this is now something QL of M minus N times delta S. Okay, and there's quite a bit to check here, namely like that this actually lives in the correct group. So what you have to do is, so this lives in ZL of 1, this lives in QL of M minus N, this lives in V of M, and now you add to get something like N minus 2M minus 1, and that equals 0. So that's why this lives in V. Okay, so what is this saying? This is saying that these sigma S's act as transvections. So they take X and they add on one of these sort of canonical basis elements to X, maybe times some number. Okay, so this is sort of the complete description of the cohomology of Lefschetz pencils. So next time I'm gonna kind of recall this and then give a bunch of examples to try to understand what's going on. We're not going to be able to prove all of this because it will involve a sort of actual I mean, I sort of gave you a very cheap definition of vanishing cycles, but to actually reduce these to local computations, one needs a sort of better notion of vanishing cycles, which is local on the source of a map rather than the target of the map. And we're not going to be able to do that in this class. So maybe what I want to do for the next 4 minutes is take questions on this sort of very complicated story, and then with the knowledge that we'll go into sort of we'll do an example next time to see what's actually going on. So does anyone have any questions about this claim? All right. Well, I don't think there's anything interesting I can say in the next 3 minutes. So maybe let's end class now, and I'll stick around in case anyone has questions that they don't want recorded. So I'm going to stop recording now.